Thank you so much for this very humbling introduction. I hope I live up to the presentation. Okay, I can skip all this now, and but the main point is that yes, I'm a computational linguist, and I am really, really grateful for this opportunity to discuss the large language models and the claims of emergent properties outside of my own disciplinary bubble. What you're going to hear is largely based on a position paper which I co-authored with Sasha Lucioni. It was published at ACML this year. And I'd like to discuss, okay, why do we need to talk about emergent properties at all? And what do we actually mean by this? And what evidence do we have that they exist? And what methodology do we need to settle the matter one way or the other? But first, before I bias you any further, I'd like to know what you think. So if you could go to menti.com using this code or scan the QR code, could you please vote in this mini poll? Interesting. It's an almost uniform distribution. I cannot see how many people are in the room. Could one of the organizers let me know if it's roughly? Okay. Okay. Okay, thank you very much. Okay, so we have a roughly uniform distribution on this matter. Now, what do you think that most NLP people think about this? Do you think that most people who work on language models think that they do have such properties, or that they don't have them, or are you not sure? Also approaching a uniform distribution. Very interesting. Okay. Now, whatever you thought when you answered those two questions, what was your idea of emergent properties when you answered those two questions? Did you think of them as something that was learned without explicit training, or just something that model learns, or something that only big models learn, or something else? These are the major definitions which I will come to discuss later. These are the ones that are mostly used in NLP literature, and come to rely on some other definition. Very interesting. I think this is the first audience I polled that has the majority definition number 4. Okay. Now, okay, why do we need to figure this out? Why do we need to talk about this? Emergent properties have earned the large language models quite a few headlines. One example is this episode in 60 Minutes in which a senior Google executive said that their model was translating from a language that it was not trained on, except it was almost certainly not true. If you search for emergent properties of LLMs on Google Scholar, you will find no lack of preprints for anything, any property of your choice, presented as an emergent property. And of course, this is a discussion with big implications for the debate about the risks of AI models. As you are probably well aware, there's one group of people who believes that the language models are about to take over the world. And there's debate that that's possible, but very much focusing on the risks that these models do already present and the harms they already inflict, such as misinformation and misrepresentation and other things. My point is that whichever version of AI risks you could subscribe to, it would be very much in your interest to know whether emergent properties exist, because this impacts the vector of responsibility for any harms that may come from these models. And especially if you believe that they could end humanity, you would very much like to know whether this is a result of how they were trained or designed, and then who bears responsibility in this case. And of course, the hype that they entrench has implications for the policy making. This is a tweet from a US senator who said that ChatGPT taught itself to do advanced chemistry. And then this is a counter tweet from a professor from Santa Fe Institute who had to say that this was completely misinformed. The point is that when professionals say emergent properties without defining them precisely, the wrong people might get the wrong idea, and then we might get the wrong regulation as a result. So it's a relatively high impact discussion. So what are we even talking about when we say emergent properties, and what do we actually know about them? So let's start by what do we mean by this? I went through some NLP and machine learning papers, and I tried to identify the major senses in which people seem to use this term. And the four main ones that I found are these. The first one is that's a property that a model exhibits despite not being explicitly trained for it. So, for example, the few-shot learning is discussed as an emergent property of GPT-3, neither specifically trained for nor anticipated to arise, to be more precise. Another definition is that completely opposite to the first one, something that the model learned from the pre-training data. So it's something that the advantages of the pre-training is discussed as emergence. Another definition is that this is something that only large models do. So if a small model doesn't do something, but then a big model does it, then it is emergent. And that definition is illustrated with empirical data such as this. On different tasks on different sizes of models, and if the big model does something and the small model doesn't, then this is emergent. And then there's a twist on this definition in which the focus is not on what is big or small, but on the sharpness or unexpectedness on this transition. So let's consider this as a separate definition. So, okay, now let's think a bit more about this. When we say that emergence is something that happens because of the training data, it seems to me that we can just say learned property. This is exactly what we expect machine learning to do if it works well. And then we do not mislead any senators by our terminology. The definition 3, something happens in big models, but not small. Here, the twist is that, okay, why is it actually working this way? And what if a small model can do whatever it is that the big model does, but if you just ask it nicely? So, for example, there's work that shows that you can induce something like few-shot reasoning in models of bird size. So then the question is how much extra effort are you allowed to put in to make the small model work as well as the big one? And also, okay, why is this happening? If the model does it because it learned it from the training data, then this is strictly to be expected. The larger model has more capacity to learn some patterns from the training data, so you would expect that it is more likely to do something that the small model cannot do. And if it doesn't, if it doesn't come from the training data, then actually we fall back on the definition 1, because this is actually the important part of this. And for the definition 4, the unpredictability part. Jason Wei himself acknowledges that if we had more data points for experiments for intermediate model sizes, not just 13 and 70 billion and 150 billion, but also, let's say, 100 and 110 and 120, then we would likely see a smooth rather than abrupt transition. And furthermore, here's a paper that was a NeurIPS oral last year that showed that actually this sharpness is an artifact of the discontinuous evaluation metrics rather than the models themselves. On these definitions where you say that, okay, it is emergent if you cannot predict the performance of the larger models from performance in smaller models. And this seems to be dubious because, okay, performance is predictable if you know that the model has sufficient capacity and you know that it was trained for the kind of stuff that it is tested on. And Jason Wei gives as an example the predictable scaling in GPT-4. But that's clearly an example where the company clearly knew what the test would be, and they specifically tried to make scaling predictable by optimizing for the things that they wanted. So it's, of course, very impressive technically, but hardly surprising theoretically. And then you would say that it is not surprising, that it is surprising if you don't know whether there is such train test overlap. And that would be the case for all these unexpected jumps in performance for big bench evaluation, which was presented in the paper Emergent Abilities of Large Language Models. So in this case, the test data was not explicitly optimized for during training. Okay, then we have our own the definition 1 to fall back on. So this is something that the model does despite not being explicitly trained for it. And here I would argue that we simply cannot prove that this is the case without analysis of pre-training data. If we want to postulate that we have a unicorn, then we have to prove it. It's on us. And of course, for models that are closed, such as GPT-4, for which we do not know the training data, we simply but I would argue that actually, even for the open models, we simply do not have the methodologies so far to do sufficient analysis of supporting evidence beyond obvious memorization. So, for example, if you have, if you train the model and you wanted to have good results on a specific benchmark, such as MMLU, let's say you deliberately create some synthetic data that looks like MMLU data and you train on it. So then you don't exactly memorize MMLU data, but you do optimize for it. Like, is this cheating or not? We need to be able to answer such questions in order to say whether something is emergent or not. And because of the complexity of this kind of comparison, I don't think we have so far conclusive evidence to say that we have real generalization to unseen data. So as an example, here's a paper that presented evaluation to unseen tasks. And these are the tasks that they listed. On yellow are in yellow color, that's the data sets that were in the training data, and in green different data sets that were used for different tasks that they used for testing. The difficulty is that there are all kinds of similarities between these data that we do not quite know and are hard to account for. So the third one from the top in the first column is a data set that is called Quail, and I happen to know about it because I made it. And I know that in this Quail dataset, there are, for example, questions that are concerned with what happens after the story is finished. So what are the plausible next things that could happen after the story? And this, of course, overlaps with the sentence completion task, which is shown here on the right. The first one, the first green block. These are all sentence completion tasks. They are, of course, based on different data, but there is Quail data that kind of targets the same kind of reasoning. So to what degree this overlaps, and does this give model enough evidence to say that now this is emergent? We simply need to define how similar it can be and what we mean by sufficiently dissimilar to be qualitatively different. And we have not done this yet. A different twist on the definition one is that, okay, maybe the model was explicitly trained on something that resembles my test data, but we didn't know about it. As long as it is unexpected to us that the model does something. And as an example of this, let's consider the way that ChatGPT plays chess. So in this example, ChatGPT plays black and Stockfish plays white. And let's just appreciate the game for a minute. So as you can see, ChatGPT makes moves that are often illegal. But of course, the fact that it can do this at all means that it can produce sequences of characters that look like legitimate chess moves. And the question here is, should we be surprised by this, given that we know that it is an autoregressive language model that was trained on data that likely contains a large chunk of web crawl, and we know that web crawl contains chess transcripts. And in this case, you would expect an autoregressive language model with sufficient capacity to be able to produce a legitimately looking sequence of chess-like moves, which is exactly what we see here. So then the question is, are we actually discovering that ChatGPT has emergent properties, or are we discovering that the internet contains chess data? And if it's the latter, then there's a much cheaper way to make that discovery. Of course, everything that I presented so far, this is the definitions that I used in machine learning, in natural language processing. And of course, emergence is a concept that has been discussed in other fields, and specifically the science of philosophy, the philosophy of science. I tried, I'm not a philosopher, but I did my honest best to try to figure out what kind of definition could be transferred over from there. And it seems to me that one way that it could be described is that if a complex system is exhaustively composed from some lower level entities, but it is not identical to them. So the example that is leading in the Stanford Encyclopedia of Philosophy article on emergence is the dust particles versus tornado, and you do not have to, and it may be even counterproductive to describe the behavior of the tornado in terms of particle physics, which can describe the dust particles. So you kind of need a different level of description to deal with the tornado as opposed to the dust particles. So does this apply to large language models? I would say yes. We can say that in trained models, we have some weight patterns, and those weights can be viewed as a kind of functional realization of whatever it is that we're trying to model. But this is a property of literally any trained deep learning model. So then if we say that this is emergence, then again, we are kind of back to saying that this just follows from the fact that this is machine learning. Another definition that I found after we did the study is that this is something that happens increasingly during training. So it's kind of about the training dynamics. Anything that the model wasn't doing before and then it starts doing as you keep training it, then this is what you call emergence. Of course, it seems to me that, again, this is implicit in the notion of machine learning as we usually have it. We do not expect that anything would appear out of nowhere. If a model learns something, then typically we get to that through the gradual process, such as gradient descent, the multiple iterations, and anything happens gradually. Another twist on this definition that the authors discuss emergence capabilities. They say, okay, although it is not appropriate to apply LLMs directly for extracting arguments, we believe that the emergence capabilities of LLMs hold promise for the phenomenon of their interest. So this is kind of saying that because these models can do anything, then they can do anything. I guess that is some kind of variation of definition one, so something that happens without being trained for, but taking it to a whole new level. Okay, so what evidence do we actually have? And I'm going to focus specifically for the evidence for the definition one, because that seems to contribute the most to the notion of emergence that would not follow from machine learning 101. Okay, so in context learning was widely discussed as emergent property that was first popularized by GPT-3. And this is one of the examples that they gave originally. So if you give the model a few examples of English to French translation, then it will be able to translate words from English to French. However, people immediately found the phenomenon of prompt sensitivity. You probably have seen yourself that the exact wording of the prompt and the order and the content of the examples you put in, they make a lot of difference, and sometimes really a lot of difference. So these are the results on two data sets for different models in GPT family from a paper, fantastically ordered prompts and where to find them. Another thing to note here is that when it's actually kind of a misnomer, because what usually happens is that people use held out data to find an optimal prompt. So you first optimize your prompt using more data, and then you evaluate in few shot setting. But if you actually had only a very few examples and couldn't tune your prompt, then in true few shot setting, the performance tends to be a lot worse. Another confounding variable to say that we have something like emergence is the instruction tuning. So most of the models that we work with nowadays are tuned to follow specific kinds of instructions. And the problem that it creates is that we don't necessarily know whether the model was tuned to follow this specific kind of prompt and this specific kind of instruction that I'm using. And here's a paper, a large scale study that considers a lot of models on 22 different tasks. And they specifically do it in a very plain setting. They don't try to tune the prompt. They give all the models the same kind of format for all data sets. And you would think that if the model truly learned to do logical deduction or question answering or whatnot, then the format of the prompt shouldn't matter that much. But what they find is basically all of the previously claimed emergent functionalities are attributable to just in-context learning. And instruction tuning, it allows the model to better use in-context learning, but doesn't seem to independently cause any emergence. What do we take from this? If the model has many fails to answer a task that wouldn't pose a challenge to a competent human, then do we deduce that it's our fault? We just didn't ask nicely, and the model could have answered this task if we tuned the prompt better, or do we conclude that the model doesn't actually have that functionality? And I realize that I'm out of time. Could the organizers let me know how much time I have?
Hi. Time is almost up, I think.
Okay. Okay, so unfortunately, we won't have time to discuss that. So I skip all this. But one thing that I'd like to show, I just showed you that there's evidence that the emergent functionality is really dependent on few-shot learning. So what about few-shot learning itself? Is that an emergent property? Because that was kind of big after GPT-3 came out. Well, here's some empirical results from the paper that I link in the slides. And what they show is that basically the model has to learn the structure of the prompt during training. So they use two conditions shown here as bursty and non-bursty. So either a uniform distribution of different characters or a structure in which different characters are repeated. So what they show is that only if you have those bursty sequences, then does the model learn to answer the questions using only in-context information. So even that seems to be not emergent according to the definition one. So how do we figure this out? Well, as I said, the first step would be to say what would we actually count as hard proof of emergence on the definition one. And let's consider again this example of English to French translation. When would you say that this is truly emergent according to the definition one? If the model was not exposed to any word lists, or if it didn't see any translated word lists, or if it didn't see any parallel texts, or maybe if it didn't see any French, in which case would you say that this is emergent? And I'll ask you this question. I would agree. To me also, it seems that I would accept that there is an emergent property of glossary or constructing glossaries if there were no glossaries in the training data. So at least the structure, I would say, is emergent. But I guess the bigger takeaway is I asked this question in many different rooms, and we don't have, even between ourselves, a clear consensus of what it would be for us to say that it is emergent. And that consensus is prerequisite to answering this question empirically. And what once we figure out what that is, what level of novelty we expect to be able to claim emergence, then we need to somehow look at the training data and figure out whether the model was exposed to that or not. And that, of course, is also not trivial, especially in the world in which all the models that people seem to care about are the closed models about which we have zero information. And even if we have this information, it's so far we don't have the methodology to answer such questions reliably. But so I'll skip this. The good news is we do start seeing the movement towards more open, fully open data sets. And there are efforts to create interfaces to make this data searchable. So I was part of the Bloom effort, and we developed a search interface for the entire Bloom training data. There's such a search for C4, and AI2 has since released Olma model, which comes with fully open public data set. So I would say we need to be more careful when we say words like emergence. We need to clarify what it is that we've been talking about. What is the hard evidence for us to say that this is real? And I'm not, of course, saying that we cannot do research based on hypotheses and assumptions. We just need to state them as such, especially in when we do research that catches a lot of headlines. So that's what I have. And I guess we don't have time for a final poll. But if we do, could you please vote? What is your position on the LLMs have emergent properties now? Thank you very much for the invitation, and thank the audience for being there at 9 a.m. on the third day of the conference. I know what it means. Thank you.